All right, ladies and gentlemen, welcome back. Long break behind us. Now we're ready to move full steam into trigonometry. Start off this quarter three with big chapter, humongous chapter on lots of very good stuff. And we're just going to go ahead and go into angles and their measure 6.1. And we're going to be dealing with two big things, basically, degrees and radians. But there's a lot of stuff to come. So let's go ahead and get started on this. So first of all, we're going to start off with angles, just our basic understandings, stuff that we've done already. So first of all, what's the question is, what is an angle? And I hope every single one of you guys can answer that. This is an angle. Any two lines, or rays as we call them, any two rays that meet at a vertex. And in here, this is our angle. We call it theta. This is theta. This is a Greek letter that we use normally to represent angles. So there are different parts of an angle as well. There are this thing here, we call this, like I just said, this is a vertex. That's that point where the two rays meet. And then when we're going to start looking at the angles, we're going to look at these two sides as two different sides. This is going to be my initial side. It's where I start. And if I measure this angle from this side up to the other side, it's where I end. And another word for end is terminal. All right, so we need to understand the ideas of initial sides and terminal sides of an angle. So initials where we begin the measuring and terminals where we end the measuring. Erase those things there. An angle in standard position, however, what most of the things we're going to be dealing with. When you're in geometry and you're measuring an angle could look anywhere you want, right? So you can draw a protractor on that however you want to do it. But here, an angle in standard position, this is when the vertex is at the origin. My initial side is on the x-axis, on the positive x-axis out here. And the terminal side is just somewhere out here in one of the four quadrants. Okay, so this is my terminal side. Somewhere out in space. I'm going to remind you guys that this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So this is an angle in standard position. It doesn't matter where that terminal side is, as long as the initial side is on the positive x-axis. And so we would measure in this direction normally. Let's say this might be 130 degrees, just because. Okay? It might not be that, but that's not the important piece here. Sorry about that. Let's get that back here. All right, so we have positive and negative angles. So if we were to take an initial side here and we were to measure counterclockwise, or CCW, some people abbreviate that. A counterclockwise angle is positive. So we would say this is a positive 130 degrees. However, we can measure in a negative direction if we were to measure clockwise. If we were to measure this direction, so clockwise, this is a negative angle. So measuring clockwise is negative. All right, so that's pretty basic. Initial side on the positive x-axis. Positive angles measure clockwise. Negative angles measure, positive angles measure counterclockwise, and negative angles you measure clockwise. Erase this stuff here. Why is it doing that? Wish it would stop. All right, so we have this other thing called coterminal angles. This is something that's probably new to you, but it's a very basic word. Very basic word. It's coterminal. Well, we know what terminal means. Terminal is the ending side, and co just means together. If you cooperate with somebody, you're working with somebody. So coterminal just means I have the same terminal angle. So if I was to have an angle that was, here's my initial side. Let's say this is a 45-degree angle. Well, that's not the only name that we could give this angle at all. We could give this name many different names. If we were to measure in the negative direction, let's say this is the actual angle here. Well, this is also measured in negative degrees. This is negative 300, oops, not 45, 315. Not doing very well here. 315 degrees. All right, you might notice that 315 plus 45 is 360 because one full revolution is 360 degrees. All right, but what if I measured, that's not the only name for it either. What if I was to go like this? Let's start here and go all the way around and come back. Well, I've done a full 360 and another 45, so this would be a, what is that? That would be 405 degrees, 360 plus 45. So these three angles here are all coterminal. And some of you guys that are thinking harder here might understand that there's infinitely many coterminal angles to this particular line. All I would have to do is just add 360, so that's what this green line was, plus 360 degrees to that original angle. Or, as I did in the red angle, I minused 360 degrees from the original angle. And you get all these coterminal angles. You just keep adding 360, subtracting 360. You just get a whole bunch of different coterminal angles. Now I'm going to ask you these two little questions here just because I want to make sure that we understand them from our geometry lessons a couple years ago. Complementary means sum to 90, and supplementary means sum to 180. There are a couple things that we need to know that just show up every once in a while. All right, so that's our basics of angles. Let's go ahead and get into degree measures. I've been using degree measures actually because they're familiar to us. One full revolution, if we were to look at this, if we were to look at this as our initial side and also our terminal side, we could say this is 0 degrees. But if I was to do one full revolution, that would be the same thing as 360 degrees. So one full revolution is 360 degrees around a circle. I'm going to answer this question in a slightly different manner here. If I was to go halfway around the circle, that would be 180 degrees. If I was to go a quarter of the way to the circle, that's 90 degrees. And if I was to go 3/4 of the way around the circle, that would be 270 degrees. So quarter revolution, half revolution, and 3/4 revolution. Those are what we call, they're actually called quadrantal angles because they're on the quadrant. They're on the line. And what we're looking at really here for this question is quadrants of all the angles. You'll notice here that the angles from 0 to 90, oops, let me get rid of that there. The angles from 0 to 90 are in quadrant 1. The angles from 90 to 180 in quadrant 2. The angles from 180 to 270 is in quadrant 3. And the angles from 270 to 360 are in quadrant 4. So very simply, if I was to say, hey, where's 210 degrees? 210 is in quadrant 3. Where's 390? That's a little bit harder. So we go 360 plus another 30 to get to 390. We're in quadrant 1. All right, so you remember in geometry, you dealt with these things we called special angles. All right, so special angles in geometry were, if you recall, a 45-degree angle, because you could create a 45, 45, 90 triangle. We had a 60-degree angle, and we had a 30-degree angle because you made the 30, 60, 90 triangle. So these are our special angles. And I'm going to go ahead and just go and do this. They don't just show up in quadrant 1. If we were to think about this being a 60-degree angle, we could actually just continue this pattern all the way around. Here's 30, 60, 90. Here's a 120. These are our new special angles that are going to go along with trigonometry here. 135, 150, and you'll notice there's 3 of these special angles in each quadrant because we're going to reference them as basically being these 3, 30, 45, 60. We'll get to that a little bit later. Okay, so 180, 210, 225, 240, 300, 315, and 330. So these are our special angles for trigonometry. They're ones that we're going to be becoming very familiar with in both degree measure and radian measure coming up. Okay, so those are one full revolution on a circle that we're going to be becoming very familiar with, the 30, or all of these numbers really. But mostly quadrant 1 is where I want you guys to be focusing for now, or a little bit. All right, so let's look at radian measure. So this is the new thing for us, something so new you've never even heard of it for the most part. So in higher level mathematics, this is another way to measure angles, and it's most commonly used in classes above Algebra 2. And since you're in a class above Algebra 2, it's time that we start using them. Okay, so here's the basic definition of a radian measure. 1 radian is the measure of the central angle that intercepts an arc equal in length to the radius of the circle. Now that is a mouthful, but you understand that in degree measures, 1 degree, so I'm going to write this here, 1 degree is just equal to 1/360th of a revolution. You go around in a circle, you turn full around, you go 360 degrees. So 1 degree is 1 out of 360 of a full revolution. Now the thing is here, with radian measures, it's measured differently because you can't just measure them everything the same, right? So if you have this radius that is r, and it comes up here like this, somewhere in here, and this is r, the central angle, meaning it meets the vertex is at the center, by the way, central angle theta, this theta is equal to 1 radian, or 1 rad, if this arc is equal to r. So the radius is the same length as what we call the arc length. Now that's kind of interesting because then we can start looking at how does this compare to degree measures. Well, one of the basic things you learned in geometry was how many times does the radius go around a circle? And if you've never asked this question, you've certainly used it plenty of times. You know that to go around a circle is circumference. And circumference is 2 pi r. That means to go around the circle, the radius goes around 2 pi times, or just a little bit more than 6. So if we were to continue this, and there's an r, there's an r. See if I can do this well enough here. It's kind of hard to cut this in half, or in these different sections here. I think this goes here. I could be wrong. And here. So you notice it goes around 6 and a little bit more. It goes around 2 pi times. Well, that's very, very helpful for us. Because one full revolution, let me get rid of some of this stuff here. One full revolution in radian measures is 2 pi radians. Now, some of you are asking, well, why is that useful? Because now we can compare radians to degrees. If one full revolution for radians is 2 pi and one full revolution for degrees is 360, we can make a comparison. Oops, sorry, I forgot that I had that there. Let's go back just a little bit, erase this. So one full revolution is 2 pi radians, and half a revolution, that would just mean pi radians. Okay, so keep that in mind here as we move forward. In order to convert, that's the comparison that we need. Since one revolution in degrees is 360, one revolution in radians is 2 pi, that means 360 degrees is equal to 2 pi radians. Or in other words, the one that we most commonly use is the fact that pi is equal to 180, which makes it very, very simple for converting. If you were to go from degrees to radians, let's say I wanted you to change 120 degrees into radians. If I wanted to change 120 degrees to radians, I would have to multiply by pi over 180. Now, pi, for the most part, is going to be left alone. Don't multiply this in your calculator, because a lot of these numbers are going to come out and simplify nicely. So I get 120 pi over 180. If you were to reduce this, this becomes 2 pi over 3. So that means 120 degrees is equal to 2 pi thirds radians. So if you were to go back to your circle that we had 120 degrees on there, that dash, that tick mark, would also equal 2 pi thirds. But what if I gave you radians? Well, if I gave you radians, let's say I gave you pi halves, pi over 2. Well, I would multiply by 180 over pi. And if you are in chemistry, if you remember chemistry, this is basic unit conversion. Notice that the degrees would cancel and you're left with radians. Here, the radians are going to cancel and you're left with degrees. So I get pi over pi, that cancels. And 180 over 2 is 90. So that means pi halves is equal to 90 degrees. All of these conversions are super, super handy for us. And we're going to be filling out a circle here soon in class sort of thing. And it's going to get all of our special angles as radian measures, all of our special angles in degrees. We already have the special angles in degrees, but we're going to use that circle a lot coming up. All right, another little thing we're going to deal with here is what we call arc length. Now, you should know that arc length is, by definition, the length of an arc, right? So it's an angle that cuts through a circle, and that being the arc length there. The formula is really simple. The formula is S equals R times theta. So S is the variable we use to represent arc length. R is obviously radius. And theta is the central angle. So if we were to look at basically a circle, if I was to cut this with an angle, here's my theta, here's my R, and here's S. So the length of this arc is what we would be finding. If your theta is already in radians, so please make a note of this. This is super, super important. Everybody seems to mess this up. If it's in radians, all you have to do is S equals R times theta and get some length. If you're in degrees, if your theta is in degrees, you must use this slightly more complicated one. But all it is taking your theta and converting it to radians. So notice this conversion factor. So if I said, really simply here, if this is my arc, and if I said R equals 6, and theta equals, I don't know, pi over 6, we could figure out arc length. Let's say this is 6 inches, like a pizza slice. So I could say S is equal to 6 times pi over 6. Here, in arc length, you actually do want to multiply by pi, but 6 divided by 6 is 1, so you get pi, which is 3.14 inches. So my arc length, the length of the crust of my pizza, is 3.14 inches. All right, moving forward. Last little thing here, linear and angular speed. Linear speed, this is a speed along if you were to have a wheel and on your bike, and you had a wheel on your bike and then you had a nail in your wheel, but you were still moving forward, you could actually figure out how fast that nail is moving around the circle using arc length. Because it would be moving along an arc, obviously rotation, rotation, rotation a whole bunch of times, but you could figure out the linear speed, how fast is that nail moving, by just doing arc length divided by time. So how far did it move on the arc length divided by how long it was going. And then lastly, angular speed, you could figure out how fast did it change from here to here, so from point A to point B, by doing the theta over the time that it took. That would be your angular speed. All right, not many of these two problems here, so this is basically a brief page just to display how you find those two things. I'm going to leave you with this. I'm going to put down in the comments somewhere a link for the PowerPoint and a link for the assignment sheet, even though you guys all have one here coming up. All right, have a good day, study hard. I'll see you guys in class.